So we have to do many things to create one of these breach models in an engineering acceptable form. So it all begins with the data preparation, and in particular, remote sensing data and the other GIS, the geospatial information that we can get. So we start with a FEMA 100-year Zone A floodplain boundary. Now, we have that somewhat as a guide, basically, because that kind of tells us when we have to stop routing the breach event. As soon as that breach, the breach waters get contained within that floodplain, it's assumed, analyses that involve that floodplain take over, and we can go, all right, we've taken it far enough, we've moved the floodway downstream enough that we're more into known territory again. Then we definitely need the most recent aerial imagery. This will be for identifying points to survey, including hydraulic structures or bridges or culverts, and then also these hazards that I mentioned. And then finally, which is really the key piece to doing all this modeling work, is having very good elevation data. We get that with the LiDAR elevation data that we have worked on for years acquiring from the state. Now, I say we, I've been kind of on the side just talking to people who are involved with that acquisition, but they've done a very good job. And here's the current coverage and potential coverage that we have slated for the state. Most of these data are actually going to be down to a 1 meter pixel something. So for every 1 meter you see in that shaded and colored area, in the cross-hatched and colored area, you will have an elevation value, and it'll be accurate to about 6 inches, plus or minus, at least 90% of the time or 95% of the time, whatever the criteria may be. These areas are in process right now. A lot of this central and southeast or northeastern part of the state are being QA'd right now. And so this database, within about a year or so, this is the kind of coverage we'll have for the state. I believe the intent is to just keep moving along and see how much of the state we can get going or get covered. Okay. So there's our data. Now we need to determine some things prior to running the breach model itself. So we'll use a climatology. Now that's just a fancy word for the 30-year precipitation averages for the state. We'll look at our site, see which precipitation zone it falls in, and then use some equations that will then tie that or relate that to a 100-year design storm, which determines, along with the catchment area for the dam, the amount of water that's going to flow through that area in the event of the 100-year storm, which is kind of a made-up thing, but it's something to hang your hat on when it comes to doing studies like this. We'll route that 100-year design storm through the reservoir. So imagine turning on your bathtub and closing the drain, and now you have this constant input from your spigot. Turn it on all the way. And pretend that's the 100-year design storm. Well, that's going to fill up the bathtub, and eventually it'll start running out. Well, it's only going to raise so high, and if it hits an equilibrium point where there's as much pouring out as is pouring in, and that is the water surface elevation now we set for the lake at the time of breach. We'll use the National Inventory of Dams data, which is an U.S. Army Corps database, to get the normal and maximum storage volumes for the dam, the estimates anyway, and then we will convert those water surface elevations to a volume so we know how much water is going to pour out of there if that dam fails. And that's actually a tough exercise because we get this great LiDAR data. We see the water surface, but we have no idea what's under that surface or what volume is contained at the time of LiDAR data collection. Well, we have to do a little bit of numerical gymnastics here to obtain an estimate of the volume that's going to be contained at the time of breach. Let's just point to back here. Point to the picture over here. You see a particular lake. This is one in Leavenworth County, and if you can see the gradient of blue, that is filling up this lake. And then you see the dam face, there's a little green line, and then a spillway until it overtops. And the question is, well, we can measure the volume now that it took to go from the current lake surface to the spillover, or the amount that spills over. We can go ahead and plug any sort of spillway and fill it to the top of the dam, which is often what those max storage estimates relate to. And then we have some options as far as tying the maximum storage to the fullest the dam can be, and then working backwards, or starting at the normal storage and claiming what's in the LIDAR, blah, blah, blah. That's what's going on here in this table. So we have many options. We look at the one and pick the one, look at them all and pick the one that appears to be the most reasonable. You're going to see a term, I dare say, best professional judgment. That's just a cop-out term, meaning somebody has to make a decision that makes sense or makes the least amount of least sense. I don't know. Okay, so we now have our water surface elevation, our volume at the time of breach. We're going to use the National Inventory of Dams to get the dam height, which is another parameter that's needed. We're going to use the LIDAR, survey data, and best professional judgment to then estimate the cross-sectional area of the dam, because that controls how quickly, using some physical models, it estimates how quickly that breach will release that volume of water. It'll open up a certain rate and the water will pour out, and the rate at which it pours out is determined by that dam. Then we use NRCS, a couple of technical reports that tell us what to do to get the peak discharge value based on those dam parameters and the volume, and then also the hydrograph equation that we'll end up using. Here's just a couple of pages from the technical reports. No tests later, so ignore. Now we've got everything we need to begin preparing and running the HECRAS model.